Assalamualaikum and good day. So today we're going to learn about the rest of the binary codes, which is the BCD, binary coded decimal, gray code, alphanumeric, ASCII code, and Unicode. Okay, first let we consider BCD codes. Okay, what is BCD code? BCD code is binary coded decimal. Okay, so let me consider this table here. To represent decimal digit, at least 4 bits must be used, since 4 bits can store up to 2 to the power of 4, which is 16 values. And only one combination is used for each decimal digit. 6 combinations are considered unused or invalid. Okay, 3 of the most common BCD codes they are used, which is BCD 8421, BCD 2421, and access 3 code. Okay, so let me discuss actually how we get this BCD code, BCD 2421 access 3, with respect to the decimal values. Okay, how we obtain the equivalent 0 decimal value in this system, or in this system. Okay, let us consider this first. The BCD 242, the BCD 8421 is so widely used, it's simply referred to BCD code. Okay, let's say you get question BCD code, it doesn't mention what detail, more, there's no detail other than that, so it simply means BCD 8421 code. Okay, so in this BCD 8421, it's simply a direct conversion from the straight binary system. Okay, let's say you see 0, the equivalent binary 4-bit is 0, 0, 0. For 1, 0, 0, 1, 2, 0, 0, 1, 0, 3, 0, 0, 1, 1, until 9, it is 1, 0, 0, 1. No different. Completely the same as the direct conversion, okay, from the straight binary system. Okay, things go a bit different when you use BCD 2421. Okay, BCD 2421 is also a weighted code with reflecting and self-complementing property. Okay, if a number has more than one representation, the code with lower binary weight is used. Okay, so what does it mean? Okay, let me consider this case. Okay, we try to see from this which have different values which have different representation. Okay, you see, this one is the same, 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 this one is the same. Okay, so let me consider number 5. Let us consider this then. Okay, what does it mean by if a number has more than one representation, the code with lower binary weight is used? Okay. You see, this is your binary weight. Okay, so you see in this binary coded decimal, the standard one, this one 4 plus 1 you can get 5. Settle. How about this one? This one, you see the possibility. First possibility is that you have, okay, we take here. First possibility to get 5, you have 0, 1, 0, 1. Am I correct? This one you will get 5. What is the other way that you can get 5? Is 2 plus 2 plus 1, right? So you have 1, 0, 1, 0. This is the other way of how you get 5. Is there any other way you can get 5? Can you tell me? Okay. Now the other one, so this is to get 5, right? 2 plus 2 plus 1. Okay. So from this you can see there is at least 2 possibilities here to get a value of 5. Okay. So which to be selected? Okay. This is where it says the code with lower binary weight is used. Okay, you see this one, it used code of binary weight 2, 2, 1. It's much lesser than this binary code weight of 4, right? Lower binary weight. Okay, so that's why we choose this one, 1, 0, 1, 1. Okay, rather than we chose 0, 1, 0, 1. Okay. How about this one? How about this code then for the 6? It's different as well, right? This one is also different. This one different. This one is different. Okay, so I want you to try this at home to see how you actually have the equivalent BCD 2421 to the decimal values. Okay, based on what you have learned in this lecture. Okay, I repeat, for BCD 2421, if a number has more than one representation, for example this case, number 5, the code with lower binary weight is used. Like here, we have 2 possibilities, this one and this one, right? But this one, the binary weight is 4 and the other binary weight is 1. The other combination, you have binary weight 2, binary weight 2, and binary weight 1. So, we chose this one because it has the lower weight. Okay? Now, we go to the next the next code, which is the excess tree. The excess tree is derived by simply adding 3 to the original decimal values. Okay, for example, you have 0. What is the excess tree? Excess tree is actually you just add 3. Okay, so what number you have here? You have 3, right? Then you convert this to the binary. What is the equivalent binary? 0, 0, 1, 1. Simply because of 2 to power of 0, is actually 1. 2 to the power of 1 is 2. So 2 plus 1, you get 3 base of 10. So it's just simply adding 3 to the original, then convert to the binary. The same as this, 9 plus 3, you get 12 to the base of 10, right? What is the 12 base of 10 in binary system? So direct conversion is just adding 3. Okay. Now we go to the next code, which is the gray code. Okay. Okay, it mentioned here is that the gray code is a non-weighted code where two successive values differ in only one bit. Okay, so you can read the detail yourself. Okay, now let me see the example. Okay, so this is your decimal values, this is your binary values, and this is the equivalent gray code. So how we have this value we will discuss later on. This is a 4-bit gray code. Simply you have 4 bits. Okay, now let me see how we actually convert from binary to gray code. Okay, okay, from here let me take one value which have different. This one is the same, and how about we choose number 2. Okay, decimal value 2, 0, 1, 0. So what is 0, 1, 0 in gray code? Okay, it's just simply you convert by, you take down the 0, then this one you carry forward here, and this one carry here, take down, then you add them up. 1 plus 0, you get what? You get 1. Okay, then also doing the same process. 1 you put here and adding with 0 here, so 0 plus 1 you get 1. Okay, so that's why for here the 0, 1, 0 binary value in gray code is 0, 1, 1. Okay, you can try yourself for the rest of the example here. Okay, see if you get the same answer. Okay, and then here is mentioned that the gray code algorithm is given by the expression gi equals to bi exclusive OR operator bi plus 1, which is a single bit addition with the carry discarded. Okay, what does it mean? You know, right, when we do the adding in the previous lecture, we know that when we do the addition, one of the operation have carry. For example, this one. So in this gray code, single bit addition, okay, when you have the carry of 1, it is discarded. So don't worry if you don't understand, we will discuss further. Okay, now let me see for the example 3.2 here. Find the gray code corresponding to binary 0, 1, 1, 0. Okay, 0, 1, 1, 0, the binary. Another conversion is that we can do by adding the original binary number with the same binary number shifted 1 bit to the right. Okay, you see this one is the original number, right, that we want to convert to gray code. Now we adding this number with the same number but shifted to the right 1 bit. Okay, for example, here you shifted to the right, then you will have 0, 1, 1. Okay. Here 0 plus 1, you get 1. 1 plus 1, you get carry 1 sum 0, right? So carry is discarded, so you only have 0 here. Discard the carry, so you don't have to carry the 1. And then the next one is 1 plus 0, you get 1, and 0 is 0. Okay, so this is another way to convert, okay, where you adding the original number with the same binary number shifted 1 bit to the right. Okay, so 0110 binary is actually equivalent to 0101 gray code. Okay, now we also need to consider the vice versa case. Let's say if you want to convert from the gray code to binary conversion. So how it goes then? Let's say we take the same number here, 0101. Okay, we take down 0, we add together 0 here. What we get? 0 plus 1, you get 1. Then this one, you bring here, add together with 0 here. Then what value you have? 1 plus 0, you have 1. Okay, then the same process repeated. 1 plus with 1 here, what you have? Zero. Okay, so the same 0101 gray code is equivalent to 0110 in binary numbers. Okay, the next chapter, okay, the next subchapter is the alphanumeric codes. Okay, we're going to study about ASCII code. The most common alphanumeric character set is 7-bit ASCII, which is stand for American Standard Code for Information Interchange. Okay, table 3.4 show the ASCII character set. Okay, here you don't have to memorize. I think you don't need to memorize this. Okay, so we simply want to know, for example, what is the ASCII code for letter, we just random, letter R. Okay, what is the ASCII code for the capital R? You see here, you just simply take bit 6 to bit 4 is 101. Then you combine with the corresponding bit 3 to 0, which is 0010. Okay, so R what is in the ASCII, what is the equivalent value in ASCII code. Okay, so it's 1010010. Okay, in base 2. So remember, you observe, you notice that it is 7-bit, right? Because read here, it is 7-bit. Okay, so your answer in 7-bit for ASCII. Okay, now we go for the next example. We go to the next sub-chapter, which is Unicode. Okay, Unicode is sufficient for using computer in the United States, but it cannot be used for all other character in other region. For example, the ASCII code standard here, the ASCII code here doesn't cover, for example, the value of the symbol for euro, or what is here is I'm not sure what it is. Okay, it doesn't cover for euro, for example, symbol euro. So that's why we use Unicode. Okay, Unicode is a computing industry standard for representing text in most of the world language. Okay, Unicode is constantly changing as more characters are added. Even today, a few characters in Jawi are still not included in the standard. Okay, so Unicode is actually to complement ASCII. Okay, because ASCII doesn't represent all symbols. Okay, now you can read this further later on yourself. Okay, you see from the table 3.6, you can see this is the character. For example, the symbol of dollar, what is the binary code point? What is the binary UTF-8? What is the hex UTF-8? Okay, okay, now the next we go to the error detecting codes. Okay, why we need error detecting codes? Okay, error detecting codes is that sometimes happen when you transmit data or containing information over long distance, or if you store an information for a long period. Okay, the information may or may not be altered. Okay, in the event that it is altered, we must able to detect it. Okay, that's why we have here error detecting code. The simplest method is to repeat each bit. For example, if you transmit bit X, you transmit double of that, which is XX. If the receiver get 2 different bits, it requests retransmission. Why? Because you see, you should have received XX, not you receive XY, something like that. Okay, this is error detecting code, since it allows 1 bit error to be detected. Okay, 1 bit error, but it is not error correcting. Like I say, it's only for detecting only. Okay, now we go for the parity codes. Okay, this one you can read yourself. Parity code checking is the simplest form of error detection. It can be extended to more advanced error detection and correction codes. By definition, a bit string has odd parity if the number of 1 in the string is odd. A bit parity has even parity if the number of 1 in the string is even. Parity checking detects odd number of bit flip but misses even number of bits because because after an even number of bit flip, the parity is still the same. You can read this later on yourself. Okay. Now let me see how we use S key with even parity. Okay. Okay, we see from the first definition, a bit string has odd parity if the number of 1 in the string is odd. Okay, first we find which of these characters have a number of 1 in the string which is odd. Ganjil, okay. Kita cari, we find this one, number of 1 is even, so this one is odd. So we take A. So the S key is 1 1 0 0 0 0 1. Okay, it have odd numbers of 1 in the string. Nombor ganjil. Ada 3 nombor 1 saja dalam string ni. Okay. So what we do? So we add 1. This is the odd parity. Okay. We add 1. So this is your S key. With even parity. Okay, the next definition is a bit string has even parity if the number of 1 in the string is even. So let's search which character have an even number of 1 in the string. So S, we have 1 0 1 0 1 1 0. How many number of 1 you have? 1 2 3 4. Even numbers. So what is the parity? So you have even parity. So you add another 0 here. Okay, because number 1 in this string is even. Okay, so you add 0. The same goes, you can try for the rest. Okay, you can try for the rest of this. For example, you have 1 is even number, right, of 1. Then you simply add 0 here. Okay. Now, okay, this the extra decimal code with more than 4 bits. Okay, decimal values 2 out of 5, biquinary. Okay, you can try this. Okay, that's all. You may try to solve this question. I don't have the answer yet, okay, but the important is you get the working step correctly. Okay, thank you very much. See you in the next lecture.